Let's do another binomial problem now. If you turn to about page 120 in the course packet, let's do problem 2. An election is coming up next week and promises to be very close. In fact, assume that 55% are in favor and 45% are against. Now, the first thing you want to note about this is that there's a dichotomous situation. So people are either for or against this, and that's a hint that this could be a binomial problem. Let's read ahead to part A. So part A says, suppose that you conduct a poll of 791 randomly selected likely voters. Find the standard deviation of the percent in favor of this poll. So notice we are repeating this experiment of asking 791 people whether they're for or against, and then we're going to be counting the number of yeses and dividing by n to get the percent. So that makes this clearly a binomial problem. Now let's go take some notes on this. So if we go over to the sketch pad, pi is the symbol that's usually used for percents, and we know that 0.55, 55% are in favor. So the percent in favor. Now in part A, we're told that we have a sample of size 791, and we could define XB as the number of those in favor. Number of those in favor. I forgot the of those, but that's okay. Out of 791. So we call up 791. We're trying to forecast who's going to win this election. XB is the number of yeses. P, which will be XB over N, is just going to be the percent of yeses, or those in favor. Let's go back and read the problem a little bit more closely. We're told to find the standard deviation of the percent. So those are the key words right there. Standard deviation is telling us that we're after a sigma, and the percent means that it's a sigma sub p. So what we're after is sigma sub p. Now how do we find this? Well, go to the slide that has all the formulas for the binomial, and here is the formula. It's just pi times 1 minus pi over n. That's the variance, so we have to take the square root of that. So let's go write the formula. This is going to be pi times 1 minus pi all over n. So let's go fill in the numbers. 0.55 times 0.45 divided by 791. Now this is equal to, I'm going to call it 1.8%. So the standard deviation of the percent is 1.8%. Now let's go back to the course packet and see what else we have to do. This comes from Siegel, by the way. So compute pi plus or minus 2 sigma sub p. So why do we want pi plus or minus 2 sigma sub p? Well, this is going to give us a region where 95% of the time when we do this poll, we'll get a number in that window. So recall that binomials are approximately normal as long as the sample size is large enough, and 791 is certainly large enough. The mean of this distribution is going to be 0.55. This is the distribution of p. Now if we go 2 standard deviations up, so 2 standard deviations is 3.6%. So that brings us up to about 58.6%. On one end, on the other end, we're at 51.4%. Now, let's talk a little bit about the result. Presumably, we're trying to forecast whether or not this thing will win. So is this ballot, referendum, whatever it is, going to pass? And recall that it will pass if it gets at least half the votes. So somewhere out here is 50%. So here we think it will pass. Whereas to the left of 50%, we think the initiative will fail. All right, so we guess that it will fail. Now note, however, that, in fact 55% are in favor of it, so this implies it should pass. Now, the fact that this 95% window, so 95% of the time when we would draw such samples, we'd get a number between, say, 51 and 58.6%. The fact that that window doesn't cover 50% means that we're pretty certain that we'll come to the right conclusion based on this poll. Let's go on to part B. Part B says, repeat this question, but now assume that n is only 200. Oops. So let's go back to the sketch pad, and we will find sigma sub p, which is going to be 0.55 times 0.45, this time divided by 200. This works out to be about 3.5%. Now let's go, 2 times that is going to be 7%. If I go draw another normal distribution out here someplace, again the mean is 55%. If we go 2 sigma out, notice on one end it's 48%, on the other end it's 62%. And this time, that magic number 0.5, where that's our cutoff point for declaring the winner, it falls right in the middle of that window. So there's a substantial probability that we will come to the wrong conclusion. So any number out in that tail indicates that we're going to come to the wrong conclusion about this election. So given that 0.5 is contained to this interval, what we're going to say is the election, is too close to call with the sample. We could call it when we had a sample of 791, but when the sample size decreases, it's just simply too close to call. Let's go now look at part C. So part C says repeat the first question, but now assume that n is 200 and pi is 0.6. So let's go do that. We have n still 200 as it was in the previous part, but now pi is 0.6. Therefore, sigma sub p will be 0.6 times 0.4 divided by 200. And if you do the math, this is also about 3.5%. So 2 sigma, it's a 2 times sigma sub p will be about 7%. Now let's go draw it this time. So here's our normal curve. Somewhere out here is about 0.55. Let's go 2 sigma in either direction. Oh, sorry, 0.6 this time. So redraw that. So the mean here is 0.6. Therefore, if we go 2 sigma in one direction, we're at 53%. We go 2 sigma in the other direction, we're at 67%. And in this case, notice our value 0.5 out here someplace is not contained in this 95% window. So in part C, again, we're quite confident that we can forecast the winner of this election with only a sample of 200. So this problem illustrates some very important points that should be part of your statistical intuition. So first off, if you have a fixed sample size like 200, in part B we couldn't call it because the election was quite close. Whereas in part C, the magnitude of the difference that we were trying to detect was much larger. So 0.6 versus 0.5 is much different than 0.55 versus 0.5. So since that difference is bigger, we can call it with a sample of 200, whereas in part B we couldn't. Likewise, with a fixed pi at 0.55, we could call it with a bigger sample. The bigger sample, the tighter your estimate, the more reliable it will be. Whereas with a smaller sample size, the less reliable it will be. So I'd recommend working this problem on your own.